Hello everyone, I'm Thanatkorn. I'm here with Sunyapat and Natthawut. And today we are going to talk about two famous experiments that completely changed how scientists understand light and matter. The Campton effect and the double slit experiment. These experiments might sound complicated at first, but they answer a really simple and interesting question. Are things in the universe waves or are they particles? As it turns out, the answer is, well, both.
Let's start with the Campton effect, which is all about light. Before this experiment, scientists believed that light was purely a wave. Waves can spread out, interfere with each other, and bend around obstacles, but they weren't supposed to behave like tiny objects that could hit things. In the Compton experiment, high-energy X-rays were fired at a material containing electrons. When the X-ray collided with the electrons, something surprising happened. The X-rays scattered, and their wavelength increased after the collision. This change in wavelength was important because it meant the X-ray has lost energy. At the same time, the electrons that were hit by the X-rays were observed to recoil and gain kinetic energy, almost as if they were being stuck by tiny particles. This behavior looked very similar to an elastic collision, like two billiard balls hitting each other, where energy and momentum can be conserved. Classical wave theories couldn't explain this result, but treating light as particles, called photons, could.
From this experiment, scientists realized that light must carry momentum even though it doesn't have mass. This was a huge deal because it showed that light can behave like a particle under the right conditions. The compound effect became one of the most strongest pieces evidence for the particle-like behavior of light can help establish the idea that light is not just a wave, but something more complex.
Now, let's switch to the other side of the story, where particles start acting like waves. This is where the double slit experiment with electrons comes in. In this experiment, electrons are fired toward a barrier with two narrow slits, and behind the barrier is a screen that records where the electrons land. If electrons were just particles, we'd expect to see two clear lines on the screen, one from each slit. But that is not what happens. When electrons are sent through the slits without observing which slit they go through, an interference pattern slowly appears on the screen. This pattern is made of bright and dark bands and is something we usually associate with waves, not particles. Even more strangely, this pattern still forms when electrons are sent through one at a time. Each electron hits the screen at a single point, but over time they build up a wave-like interference pattern.
This behavior can be explained using the idea of the de Broglie wavelength. Louis de Broglie suggests that all particles have a wavelength that depends on their momentum. So the faster an electron moves, the shorter its wavelength. This idea was later confirmed by experiments like the Davison-Germers experiment, which showed that electrons can diffract just like waves. Because of this, electrons don't just travel in straight lines. They can spread out like waves and can interfere with themselves.
However, the experiment changed when we try to observe the electron more closely. If a detector is placed at the slit to see which slit each electron passes through, the interference pattern disappears. Instead, the electrons behave like normal particles again and form two distinct bands on the screen. This is known as the observer effect, where the act of measuring changes the outcome of the experiment. This brings up the concept of wave-particle duality. Both light and matter can behave like waves or particles depending on how we observe them. Light behaves like a particle in the compound effect, while electrons behave like waves in the double-slit experiment. There isn't a single correct model. Both behaviors are real and depend on the experimental setup.
One common way scientists explain this is through the Copenhagen interpretation of quantum mechanics. According to this interpretation, Particles like electrons don't have a definite position or path until they are measured. Instead, they exist as a wave of probabilities described by something called a wave function. When we make a measurement, the wave function collapses and the particle takes on a definite state. In simple terms, the electron does not choose whether to act like a wave or a particle until we force it to by observing it.
There are also other interpretations, like the many worlds interpretation, which suggests that every possible outcome actually happens in different branches of the universe. While these interpretations try to explain what's really going on behind the scenes, they all agree on one thing. Quantum objects don't behave like everyday objects, and our classical intuitions don't always apply.
To wrap everything up, the comfort effect and the double-slit experiment show us that the universe at a small scale is much stranger than we might expect. Light or matter are not just wave or particle, but something that can be both at the same time. These discoveries didn't just change physics textbook, they helped shape modern technology from electron microscope to quantum computers. Understanding wave-particle duality gives us a deeper insight into how the world truly works, even when it doesn't behave the way we expect.
Thank you for listening and Happy New Year.